Hello guys, am I audible? Okay, nice. So let's start on with the PCD for the Codeforces Round 1019. The sound is coming good as well. So in this PCD, we will discuss the first four problems. And now let's start with the first problem, that is A problem, common multiples. The problem says that we have been given an array of n integers. Yeah, we have been given an array of n integers, and they say that an array x of m integers is considered beautiful if there exists some array y such that all the elements in the array y are distinct, and the product of xi and yi is the same for all of basically. If you have an array x like 1 2 3 7, then it is gonna be considered beautiful if there exists some array y such that the elements of the array y, let's say y1, y2, y3, and y4, uh, there is some possibility such that all of these four integers are none of them is equal to any of the other one. Basically, all of these should be distinct, and y1 into 1 should be equal to y2 into 2, that should be equal to y3 into 3, which should be equal to y4 into 7, right? The product of these two people should be equal to the product of these two, that should be equal to the product of these two, and it should also be the product of these two. So all these products should be equal to each other. That's what we want. So if there exists such an array y, then this array x would be considered beautiful. Remember that all the elements of y should be. Okay, so I hope I am visible now. So guys, can you please tell me till which point was I audible and my video was visible, and when did it go off? It was due to the internet connection issue. I hope it would not happen now because now I have connected to my mobile internet connection. um, can somebody please tell? Anyways, I will just start from the complete start of the problem. So um, the first problem, common multiples. In this problem, we have been told that there is an array A which is being given to us, and they define an array X as beautiful if there exists an array Y such that all of the elements of the array Y are distinct, and there is a particular condition for there is a particular condition that the product of all xi into yi should be same for every index I, which I will explain here. So let's say if you have an array x 1, 2, 3, 7, and there exists an array y. Let's say the elements of the array y are y1, y2, y3, y4, anything. Um, First of all of these four elements should be distinct. None of them should be equal to any of the other element. So something like 1, 2, 3, 4 is good since these are distinct. But something like 1, 2 to 4 would not be okay for array y. Nextly, there is one more condition apart from all the elements being distinct. The product of these two elements should be equal to the product of these two, which should be equal to the product of these two, and the product of these two should also be equal. So basically, y into 1 should be equal to y2 into 2, which should be equal to y3 into 3, and that should be equal to y4 into 7. Right. So basically, for every index I, you will just calculate xi into yi. And now what you want is whatever values you got for every I, they should be same. Xi into yi should be same for every I. So is the problem clear now? Um, yeah, that was being told to us. And what we have to answer is from the array A that is being given to us, we have to tell the size of the um, largest subsequence, which is beautiful. So basically the size of the largest beautiful subsequence of the array A. So what is a subsequence? What is a subsequence of an array? A subsequence is nothing but um, take the complete array. Now you can remove any of these elements. Like let's say I remove this. It's up to you even if you don't remove any element or even if you remove all the elements. Um, it's up to you which elements you want to remove. So the other elements that are left, um, that is gonna be known as a subsequence. So in other words, you can just say that from the array, you can pick up any elements of your choice, any subset of the elements, and keep them in the same order. So if you pick up 1 and 3, and let's say 1, 3, 7, then this would be a subsequence. Just make sure that these elements that you have picked up are coming in the same order. So that sequence of elements would be known as a subsequence. So that's it. Like this is the problem statement. So please confirm if it is clear. And is my voice and video coming good now? Is the video quality coming good now? By the way, somebody commented, "माँ मुझे कुछ दिखाई नहीं दे रहा." Sorry, not here, but he had commented somewhere up. "माँ मुझे कुछ दिखाई नहीं दे रहा" when the video was not visible. Okay, I don't see anyone saying, anyone asking any doubts for the problem statement of it. So let's discuss the logic part for the first problem. So the idea is, the first observation that I made right after reading the problem was, if um, whatever array you have, let's say 1, 2, 3, 2, 4, 7, 3, something like this, then the idea is, if you pick up this 2 and this 2 in the subsequence, um, right, if you pick up both of these, then um, you can never have any array y in which you will have two distinct elements and you multiply this two with some element and you multiply this two with some different element and you get the same product. Basically, if in the array x, you have 1, 2, 2 as the elements, then there will never exist any array y such that all the elements are distinct and um, 2 into y2 is equal to 2 into y3. This thing is just impossible, right? If you want these two to be equal, then y2 and y3 would have to be equal, and it will contradict with the condition of all elements being distinct. So what we have realized is, at the very least, all the elements of the array X must be distinct. है ना? All um, any, any array X can be beautiful only if all the elements are distinct. Nextly, if you consider any array where all the elements are distinct, then you can always form an array Y. Let's say you have an array 1, 2, 3, 4, 5, 6, 7, something like this. Then a very simple thing that you can do is, you can create an array Y such that yi would be nothing but the LCM of the array X divided by xi. So in that case, what will happen is, xi into yi will be just equal to LCM of X, array X. है ना? So you can do something like this to just make sure that the product of all the y's, the product of all the xi into yi would be same for every I. So you can do something like this to just make sure that if array X has distinct elements, then you will always have some array Y. So basically, array X would be beautiful if all the elements are distinct. So if you want to find out the largest beautiful subsequence of array A, we are basically being asked to find out the number of unique elements of X. Number of unique elements in array X, right? If you just find out the number of unique elements, then that is going to be the answer, because if the array X has 7 unique elements in it, then what you can do is, you can just have a subsequence of size 7 in which every element is coming exactly once. And um, you can't have a subsequence of larger size, because in that case you will have at least one duplicate, which will make the array impossible to be beautiful. So I hope this is making sense. Okay, so let's move on to the code and then to the next problem. So for the code of the A problem, the logic is pretty simple. Just take the inputs, put everything inside the set, and set.size would be the answer. If you don't know about sets, I would just recommend you to learn about sets in that case. But even if you want to solve the problem without using sets, you could have done something like sort the array and then traverse from left to right. And whenever you find an element which is not equal to the previous element, just increment the counter. You can do something like this to find out the number of unique elements. Or you can use a map if you want, but using a map would be just similar to using a set. So that's not really going to be very optimal or something. Okay. Um, by the way, you could have created a vector of size n as well. You could have done something like create a vector of size n and then find the frequency of every element and then find out the number of elements having frequency greater than 0. So basically, I'm just telling you about a few different ways of doing the problem. Though during the contest, you should just go with the way with the in which you feel the most comfortable, and you can write the code as fast as possible. But during the time of practice, you should actually go with all these different ways for solving easy problems as well. Um, so anyone below pupil, basically all the newbies, should try out all different ways, in my opinion. Now let's move on to the second problem, binary typewriter. So this is actually a very interesting problem. It says that we have been given a binary string s of length n, and there is a typewriter with two buttons, 0 and 1. Our finger is initially on the button 0. We can do two, uh, like there are two type of operations that we can do. Either we can press the button that our finger is currently on. So if my finger is on the button 0, I can either press that button 0. This will type out the character that is on the button, or I can move my finger to the other button. So if I'm at the button 0, then I can move on to the button 1. If I'm at the button 1, then I can move on to the button 0. Right. The cost of the binary string is defined as the minimum number of operations needed to type the entire string. And before typing, we can reverse at most one substring of S. More formally, we will have to basically just choose a substring and reverse it. So our task is to find out what is the minimum number of minimum cost among all the substrings that are obtainable by performing at most one substring reversal on S. So basically, we can apply at most one reversal on any substring of our choice, and we want to find out what is the minimum cost that we can achieve by applying at most one of these reversal operation. So is the problem clear? The problem B, in which we were just being told that there is a string, there is a binary string. Let's say the binary string is something like 0 1 0 1 1 0 1 1, or let's say 0 1 0 here. So initially our um, finger is on the button 0. So first of all, we will apply the type 1 operation to type out this 0. Then we will have to apply the type 2 operation to move our finger to the button 1. And then we can apply the type 1 operation here to type this button. Then again apply the type 2 operation to change the finger. Then, sorry, to change to the other button, change our finger to the other button. Then we can apply type 1 operation to write this. Then again we use the type 2 operation to change our finger, or basically change the button. And then we can apply the type 1 operation this character, then again type 1 operation to write this character, and then just keep on doing this. Whenever you find out a different character, like right now I just wrote the character 1. If I find out a different character, then obviously I need to apply the type 1 operation once. And once I have applied the type 1 operation, um, sorry, I will have to apply the type 2 operation to change the finger. And once I have changed the finger and I am having my finger on the button 1, then I will just type it, right? So this is how you can basically um, have the minimum cost, right? You can have the minimum number of operations applied in this way, because uh, we are changing our finger only when we have to change the character, right? If you are having your finger on the character 0 and you want to type character 1, only then you are applying the type 2 operation. And as for the type 1 operation, it will happen exactly n times because you are writing exactly n characters, right? So type 1 character will happen, sorry, type 1 operation will happen exactly n times, and type 2 operation will happen, um, like the number of times type 2 operation will happen is equal to um, number of 0 1 pairs or 1 0 pairs in the string, right? And um, you might have to sometimes apply one extra operation. Like if you have a string like 1 0 1 0 1, then in that case, or maybe let's say 1 0 1 1 1. So in that case, apart from applying an operation, a type 2 operation at this place after typing 1, and here after typing 0, you will have to apply one type 2 operation here as well before writing the 1, because initially our finger is on the character 0, right? So is it making sense? Like, are you able to understand the problem statement? So, in the problem, they are just asking us that we are permitted to choose any substring of our choice and reverse it. So, in this case, not let's say I reverse this string, it will become then 1 0 1 1 0. And after reversing it, I will calculate the cost. So the problem is asking us what is the minimum cost that we can achieve. Basically, we have to minimize the cost as much as possible by applying this operation at most once. So guys, please tell me, is it making sense? So CF handle. Um, I don't see anyone asking any doubts for the problem B, so let's move on to the logic part. Guys, like in case if anybody ever gets a problem, like while watching the PCD, feel free to ask it in the chat. For like I can't really wait one minute every time whenever I finish explaining the problem statement, or I explain some part and then want to see if anyone has any doubt or not. All I can do is I can just open up the chat and see if anybody is asking any doubts or not. So if you have any doubt, just ask it at the same time, and I will just check it out once I'm done explaining some portion, and we'll then look at the chat and we'll try to answer your doubts and then move on. So whenever you get any doubt, just ask it into the chat. Okay, so for now, right after reading this problem, the thing that came in my mind was, let's say this is the string, this is the given string that I have, or maybe I can just take a normal example, maybe something like 011 011 0 0 0 1, something like this. If I have a binary string and I decide to reverse some portion of it, then do you guys agree that all of the um like I am applying the type 2 operation only when I have a 0 1 or 1 0 pair, right? So let me mark all the 1 0 and 0 1 pairs here. I have marked all the 1 0 and 0 1 pairs like these. So do you guys agree that if I reverse this substring, then all of the 0 1 and 1 0 pairs in this part and in this part will remain the same? Like if there was a 0 1 pair here, it would still be there even after I reverse this part, because this portion is not affected, right? This portion is not changed in any way. Similarly for this portion, right? So I hope everyone does agree with it, that the number of um, type 2 operations that I had to apply in this portion will remain the same, and the number of type 2 operations that I had to apply in this portion will also remain the same. Similarly, do you guys agree that even if I reverse this, let's say I reverse this string from 10110 to 01101, after reversing it, reversing the string, it becomes like this. Um, if I had this um, alternating pair here of 1 0, it will still come here. It is the only thing that will happen is, earlier it was a 1 0 pair, now it will become a 0 1 pair. I had a 0 1 pair here, so it will come here. It will now just become a 1 0 pair. Similarly, the 1 0 pair here will just come here and it will become a 0 1 pair, right? This is something that you have to notice. So in a nutshell, the number of alternating pairs in this substring will also remain the same, right? So the only thing that is changing for now is, earlier these 0 and 1 are paired. Now this 0 is actually paired with this 0, which came from this position, basically an endpoint of the substring. Similarly, this guy who was earlier connected to this 0 will now be connected to this 1, right? So I'm connecting this 0 with this and this 1 with this, right? So can I say that the cost that would be affected by reversing this substring would be equivalent to the cost that would have been, um, or basically can I just say that I just need to keep track of these elements, these four elements, right? I just need to keep track of these four elements, because the cost is gonna be affected at these two positions only, at this position and at this position. So if um, if these elements were originally 0 1, and these elements were originally, let's say, like 0 0, then I will get rid of this one alternating pair. But when this guy will go here, I will get one new alternating pair, which was not present earlier. Earlier, these 0 and 0 were not having any trouble, but now this 1 and 0 will have, uh, will cost you one extra operation, right? So, in a nutshell, um, yeah, there is one more observation uh, that we will discuss first, and then we will move on to the conclusion. The observation here is, since these two people are still gonna be at the same place, and only these two will change. So if these two people are the same, like let's say if this was a 0 and this is also a 0, then whatever thing was happening here will still happen when this 0 and this 0 will match up, and whatever was happening here will still happen when this 0 and this 0 matches together. So basically, applying the operation will not affect the cost. Our motive is to minimize the cost. So we only want to care about the case where we are reducing the number of operations, right? Where we are reducing the cost. So shall we just discuss about the case where we are actually gonna reduce the cost? That thing can never happen if both of these people are same. It can happen only in a case like this when both of these people are different. Maybe this is 1 and this is 0, or this is 0 and this is 1, right? So we know that um, it is beneficial to apply the operation on a substring only when the first character of the substring, if it is 1, then the last character of the substring should be 0. Otherwise, if the first character is 0, then the last character should be 1. Only then applying the operation on the substring may reduce the cost. Otherwise, it won't have any effect on the cost. Now, the thing is, if you had something like 1 1 here and 0 0 here, then applying the operation will actually increase the cost. And our motive is to just reduce the cost. We just want to reduce the cost. So I hope everyone here would be able to see this, or at least get the idea of this. That I want to apply the operation in this kind of a case, where whatever substring I have, where whatever the string I have, I will apply an operation on a substring such that both these pairs are having some trouble with each other. Basically, I will save a type 2 operation here, and I will save a type 2 operation here. Do you guys agree with it? Do you guys agree with it? And let me see if anybody has having any doubt till now. What if we calculate the total cost? No, no, no. We reduce for the code, raise the total section of software. Yeah, so what if we calculate the total cost of substring and we check 0, 1, 1, 0 exists, plus minus 2, the answer. Yeah, Kavish, you are thinking on the right side. It is said at most one reversal. So if there exists a reversal without performing a reversal, the cost is already known. Yeah, you don't really need to, you're not obligated to apply an operation. And even if the problem set that you have to apply exactly one operation, you can always just choose a substring of size 1, which will not affect anything. So it's not really a problem for us. What if we calculate the total cost of the substring and check if, yeah, Kavish, you are thinking on the right side. So you just wrote the comment twice. Okay, so I hope you like Kavish, you people are also able to think that, hey, what I want to do is I just want a 0 1 pair, and like I just want a 0 1 pair in the string somewhere, and somewhere I just want a 1 0 pair. If I can find this thing, or sorry, if I can find 0 1 pair occurring twice in the string, then what I can do is I can just choose this as the substring, which is starting from the uh, one of the 0 1 first 0 1 pair, and 0 ending on the 0 of the last 0 1 pair, so that this 0 will come here, this 1 will go there, and you will have a 0 0 1 1. Basically, you will save two type 2 operations, right? Here, please note that by applying one operation, you can save only two type 2 operations. You can never save more than that. And talking about type 1 operations, you can never save it. You will always have to write n characters, so you will always have n type 1 operations. So here we know that we cannot save more than two type 2 operations. So if you can find 201 pairs in the string, or if you can find 210 pairs in the string, in that case, you can just say that whatever is the current cost, you can iterate over the string first. Like when you take the input, you can just iterate over the string to find out what is the current cost. And then you can just say that, hey, while iterating, you could have calculated the number of times there are 0, 1 and 10 pairs. You could have done something like this also. So if the number of 0, 1 and 10 pairs is greater than 2 or equal to 2, in that case, whatever answer you had, you can just subtract 2 from it. Right. So guys, does it make sense? This is one thing that we can do. If you are having this thing, then you can just simply apply operation on that kind of a substring and save two type 2 operations. And we can just see that, hey, if you swap any substring, there are only two places that are being affected. So you can never save more than two operations. So for now, this is the best that we can do. Now you would like to think about the case where you don't have two occurrences of 0, 1 and you don't have two occurrences of 1, 0. So there are only a few possibilities for that kind of substrings. It can happen if you have a few zeros, then you have a few ones, then you have a few zeros, right? You cannot have any more one, because if you have one more occurrence of one, then you will have more than one occurrences of 0, 1 pair, right? So either you can have this kind of a substring which is having some zeros, it is then having some ones, and then it is having some zeros, or you can have a type of, you can have a substring, so you can have a string with this format, some ones, some zeros, and then some ones. Something like one is occurring three times, and then let's say one is occurring four times, and then one is coming two times, something like this. Obviously, you can have only one occurrence also. Something like 101 is also a string that follows this pattern. Or you might have a string like 01, or you might have a string like some ones, some zeros, or you can have some string like having all zeros or having all ones. Right. There are only these patterns for any string that does not have um, two occurrences of 01 or two occurrences of 10 in the string. Do you guys agree with it? What's your CFIT? My CFIT is, it's Raghav. ITZZRAGH. Okay, so now let's move on. So now what we can do is we can just manually calculate what would be the answers for these patterns, like how much uh, we can reduce the cost. So if you have, let's consider the easiest case first. If the given string is something like this or something like this, in that case, no matter what substring you reverse, the final substring would still be the same. So whatever cost you have, it will still remain the same. So in that case, answer will remain the same. So answer would not be affected, right? Talking about this case, you can just swap the complete string. So you would be left up with something like some zeros and some ones. In this case, there will be only one type 2 operation required, right? So what like the answer in this case would come out to be one. You know, if you have this kind of a substring, sorry, if you have this kind of a string, in that case, so yeah, let me mark also. So here we got the answer as one. Here the answer was zero. Here the answer was one. For this substring as well, you don't really need to do anything. The cost here is right now one. That is the type 2 operation required here, and you can't do anything. You can't remove it because you will always have some zeros and some ones in the array, after whatever operation you apply. So obviously you will have to change the button at some point of time. Then talking about this, string, you will apply a type 2 operation here, then a type 2 operation here, and then a type 2 operation here, and that's it. You will apply type 2 operations at these three places. So here what we can do is we can just swap this string so that it becomes like some zeros and then some ones and some ones. So either you can call it like this, or you can just call it like some zeros and then some ones, right? Basically, it will become like this. So it will have a final answer as 1. And talking about this case, um, here also you can just swap these two substring, like you can just choose a substring like this, which is having all the ones and all the zeros at the end, so that you will have some zeros and then some zeros and then some ones. So you will have to apply the type 2 operation only once. So the answer here would also be equal to 1, right? So either you can do something like this, just like now we have actually got the answer that by taking the input, after taking the input string, you can write many if else conditions to just find out what would be the answer. Now you can just try to find out some common patterns among these strings as well to um, have less number of if else conditions and have a short code. है ना? So if I was at your place and I had thought this much, then what I would do is I will iterate over the string, find out the 0 1 pairs and the 1 0 pairs. Okay, so first of all, after taking the string as input, I will calculate the answer, basically the current cost. I will find out the current cost. And while iterating, I will calculate this thing as well. What is the number of 0 1 pairs and what is the number of 1 0 pairs? If I find out that any of them is greater than or equal to 2, then I will just simply answer that my answer is cost minus 2. Okay. So if count of 0 1 or count of 1 0 is greater than equal to 2, right? Um, then answer is cost minus 2. Otherwise, otherwise, if you like in these four cases, the like in these four cases, what you have is the number of 0 1 pairs, like the count of zero. Either you will have a 0 1 pair or you will have a 1 0 pair. है ना? At least one of these will happen or both of these will happen. So in these four pairs, you can just say the count of 0 1 or count of 0 2 is at least 1. So if count of 0 1 is greater than 1 or count of 1 0 is greater than 1, then return 1, right? And along with this if condition, you can just write that if the first character is 1, um, like if you are passing these two if conditions and failed at both of the places, then the final string should either be like this, having all zeros or having all ones. So you can just have your answer as maybe the whatever is the first character, or you can have a condition like else if the first character of the string is equal to 1, then answer is 1, else 0. You can write something like this, or um, I would have loved to just write this if condition at this place. Like if this is happening or this is happening or the first character is 1, then in any of these cases, the answer is 1. Otherwise, the answer is 0. So guys, is it making sense? I thought we have to reduce the inversions. Um, no, it has nothing to do with inversions. Even if you have a string um, like even if you have a string like 1 1 1 1 1 and then a few zeros, it is having too many inversions, right? But um, we have nothing, like we don't really have any problem with it. Um, all we want to do is we want to reduce the 0 1, like 0 1 pairs and 1 0 pairs, where these are coming adjacent to each other, right? So like the count of inversions is a different thing, though it might sound similar, but it is a different thing. In the case of counting inversions, 0 1 is considered good, but here 0 1 and 1 0 are equally bad for us. Okay, so let's move on to the code part. Now let me just give you a disclaimer. At the time when I was writing, when I was solving this problem during the contest, um, I had not tried to think about it in like this way. I was a bit hasty because during the contest, you want to solve it as fast as possible. So I thought about some stuff, then I started coding it up, then I thought about some more stuff, then I coded it up, and so on. So my code is not gonna be that clean. Um, so I had to move it. Yeah. So this is the code for the second problem, or not. This is for third, maybe. Yeah, this is for the second problem. Okay. I just thought that I might have messed up. Yeah. So this is the code for the second problem. I first of all took all the inputs. I created a few variables, first 0 1, last 0 1. Basically, with the help of um, these two variables, I will find out whether the count of 0 1 and 1 0 is equal to 1 or greater than equal to 2, or it is equal to 0. I will be able to find out the count here as well with these two variables. Though a better call is to just uh, find out the count. है ना? That is gonna be simpler to implement and to think. And the code that I would provide in the description would have the simpler solution that we discussed uh, in the PCD. Like for PCD, I had been trying to think about a simpler solution than my solution in the contest. So after this, what I did is I just found the values for these variables, and then I'm having a few conditions like uh, this condition is for the case if uh, this if condition. If the count of 0 1 or 1 0 is greater than equal to 2, then this will happen. And these if else conditions are a bit specific. And if I try to explain this, it will just make things more confusing. The better thing is just look at these if else conditions that I wrote. These are way simpler and way more precise. Um, that if the count for any of them is greater than equal to 2, then we are talking about this case where you can just straight away reduce the cost by 2. Nextly, if you talk about these cases where count of 0 1 is greater than equal to 1, or count of 1 0 is greater than equal to 1, and they are obviously not greater than equal to 2, then you are just always able to make the cost 1, either by swapping these two. If you had the string like 1 in the 1 0 pair, or if you had the string in like 0 1 pair, you can still have the cost 1. And for these as well, you are able to make some swaps to make sure that you are required to make only one operation of type 2, right? And you will obviously have to apply n type 1 operations. So um, yeah, let me correct it. It should not be return 1, it should be return 1 plus n, or basically n plus 1, n plus 1, and return n here. This if condition is talking about all this. This if else if condition is talking about these four cases, and this else if condition is talking about this case where you have all ones. You will have to apply one operation, that is changing the button before typing the first character. And the else condition where you have all zeros is just n. You will have to apply n operations. That's it. And by the way, um, Jiangli wrote a very short code for this problem because he might have noticed this. he must have noticed this, that either the cost would be decreased by 2, like the cost is always decreased by 2 if the cost is, like before applying the operation, if the cost is greater than or equal to 3, then the cost is always decreased by 2, right? In all of these cases where the count of 0 1 or 1 0 is greater than equal to 2, then you would have the cost being greater than equal to 3 always. So the cost would be decreased by 2 in those cases as well. Similarly, the cost here is also 3 and it would be decreased, and it would be decreased by 2. And in the other cases where the cost is 1 or 2, like in these cases and in this case where the cost is either 1 or it is 2, in those cases cost will just become equal to 1. So in case of Jiangli, what he did is he iterated over the string to find out the cost, and then he said that cost should be equal to maximum of cost and um cost minus 2 and 1, right? But I don't think this kind of solution is for people like us. The one that I discussed is a lot more easier to think for beginners, I believe. So we will stick to this one. Seen his code but didn't understand. I think you're talking about Jiangli. I hope you are able to understand it now once we have discussed like why his solution is going to be correct. Because either the cost would be decreased by 2 if it is greater than equal to 3. And for the cases where the cost was either 2 or 1, it remained 1. What is the approx rating of this problem? I think it should be like 13 1400 maybe, or 1200. It won't be higher than 1400 in my opinion, though it depends upon the submissions. So if there were less people in today's contest, it might have more rating. So let's move on to the third problem now. And by the way, the solution, the code with this approach would be provided to you in the description right after the PCD. Like once the PCD ends, I will write the code and we'll share it in the description. Okay, so the third problem is median splits. The problem says that the median of an array is the m by 2th seal of m by 2th smallest element of array B. So basically, if you have an array like, if you have an array B like 2 1 3 4 uh, 1, something like this, then there are 5 elements, right? Then the m by 2 seal of m by 2 would be equal to 3 here. Seal of 5 by 2 is going to be 3. So we will look out for the third smallest guy. So here the smallest guy is 1, second smallest is also 1, third smallest is 2. So the median of this array, which we define, which we for now call as MED of B, is gonna be equal to 2. This is how the median is defined in the problem. And the way which I prefer for finding out the median is just sort these arrays, just sort the array, and once you sort it, the middle guy would be the median. If let's say you have an even size array, let's say the array had element 5 also, then the sorted array would become 1 1 2 3 4 5. So in this case, you have two middle guys. So in this case, we generally, like I generally go to the problem statement to see which one they are referring to as the median. For this problem, since they said seal of m by 2, then if there are like, when there were 5 people, the median was the third guy, the third smallest. And when there are 6 people, the median is still the third smallest. So it would be the left middle guy. है ना? In case of even elements, you have two middle people. So we are talking about the left middle guy. So that's it. That is how we can find out the median. Now the problem is asking us, you have been given an array A and an integer k, we have to determine whether it is possible to partition this array A into three contiguous subarrays such that the median of um, the medians of these three partitions. So basically what we are doing here is we have an array A. We will partition it into three parts. We will find out the median of this guy, let's call it as M1, the median of this subarray, let's call it as M2, and the median of this partition, let's call it as M3. Then we will find out the median of these three elements, the median of these three people. Let's call like whatever thing that we get as the final median of these three people, we want it to be smaller than or equal to k. That's the problem. We have to tell if it is possible to partition in such a way or not. So what they have said here is just a mathematical way of telling it. And since we are actually, since right now I'm speaking verbally, so that's why it's convenient for me to just tell in this way that we are gonna partition the array into three parts. Find out the median of the first guy, median of the second guy, median of the third guy, and take out the median of these three people. We want this thing to be smaller than or equal to k. If we can achieve it, print yes, otherwise no. So guys, is the problem clear? 1125. Can we do cost equal to n plus maximum transitions minus 1 comma 1? You can try this out if it is gonna work or not. Like you can just simply try to print like try to code it in this way. So I think it would be like transitions minus 2 comma 1 instead of transitions minus 1. Okay, so let's talk about this current problem. So right after reading this, the things that came into my mind were um like if I have to tell whether it let's say if you have 5 elements and you have to tell if the median of these 5 elements, let's say x1, x2, x3, x4, and x5 can be less than equal to k or not, then one way for finding this out is just check out the number of people who are less than or equal to k. Right. At the end of the day, for finding out the median of an array, if you sort these elements in the sorted way, let's say the sorted order, whatever the sorted order is, let's say I've sorted them, then if the median guy is less than equal to k, then um, all these people would also have to be less than equal to k, right? If the median guy is less than equal to k, then the people on the left hand side of the median would also be less than equal to k, right? So in this case, when we have 3 elements and we are being asked to find out if the median of the three partitions that we can create, basically the median of medians of the three partitions that we create, if this thing can be less than equal to k or not. So my idea was I just want to find out if I can partition this array A, if I can partition this array A into three parts such that there are at least two partitions whose medians are less than or equal to k. If I just make sure that I find out three partitions, like I create three partitions in a way that two of them, at least two of them, are having their medians less than equal to k. It is fine if all three of them are having their medians less than equal to k, but at least two of them should have medians less than equal to k. So that was my goal. And for this, what you can do is, oh yeah, there is one more thing, that there is one more way of simplifying the problem. One of them is just this much. We have simplified this thing into this part, that find if we can partition the array into three parts such that at least two of them have medians greater than, it's less than, no? Yeah, less than, sorry. Have their medians less than equal to k. If we can do this thing or not. So instead of worrying about this, I will now worry about this. This is how I have simplified the problem for now. Nextly, there is the next thing, that since I only want to worry about having some subarray whose median is less than equal to k or not, my idea was that there are three type of partitionings which are possible. One of them is I have the first two partitions having their medians less than equal to k, or I have the first and third partition having the medians less than equal to k, or the second and third partitions having medians less than equal to k. So for this case, what I thought was I will just start picking up elements from the left till the point. Like basically, I will just keep on picking elements until I find out. Uh, Basically, until the prefix has the median less than equal to k. So let's say the first element is 7, then the second element is 8, the third element is 2, and the fourth element is, let's say, 1. Now, after adding the fourth element, my median became 2. So I can just, like, if let's say 2 is less than or equal to k, then I can just say that, hey, I will pick up only this um, prefix as the first partition. And now I will just start picking up elements for the second partition. As soon as I am able to reach a position where this subarray is also having the median less than equal to k, I will just stop and dump everything into the third partition, because I don't care about the third partition anymore. I will have two partitions having the median less than or equal to k. The second way, for now, let's talk about the third way first. In the third way, it is just, instead of starting from the left, we are gonna start from the right. Or what you can do is, you can just reverse this array, and whatever logic you ran on this array here to find out if you can have the first two partitions with medians less than equal to k, just run the same logic for this array once you have reversed the array, right? So we can check if this thing is possible, and we can similarly check if this thing is possible. Nextly, talking about this case, it is even simpler. All you need to do is just check from left to right, find out the first position where the median becomes less than equal to k. Similarly, run from the right side, and as soon as you find out a position where the median becomes less than equal to k, stop there. And now all you want is the elements in the middle. Yeah, by the way, this thing should happen earlier as well. If you are able to have two uh these contiguous subarrays having medians less than equal to k, the third subarray should also be non-empty. So basically, this point that you had where the second subarray ended must have ended before or on the last second element. Basically, there should be at least one element in this subarray. Similarly, what you want is this prefix and this suffix. First of all, they should be non-overlapping, and there should be at least one element in the middle of these, right? So that you can dump all the elements in the middle into the third or the middle partition. You can't do this if you don't have any elements left here. So this is how we can solve the problem, though there is just one edge case that we need to take care of, which is given in the problem statement also. Let me show you a dry run here. Let's consider this case. Okay, nice. Yeah, so let's talk about this subarray. Sorry, this array. Our logic so far, actually not this, but this array. Mhm. Okay, so by the way, please confirm if everything till this point was clear at least. Everything at least till this point was clear or not. Let me do a recap as well once. We wanted to find out if um like we would be given an array A, we wanted to find out if we can partition this array into three parts such that the medians of these, if we find out the medians of these three partitions, then the median of these three medians would be less than equal to k. Here we made one simplification. Instead of checking whether the median of these three would be less than equal to k or not, we can say that at least two of these medians should be less than equal to k. If there are two people who are less than equal to k, then the median would also be less than equal to k. Then we got this problem now that when we are making three partitions, now we want to have at least two partitions with median less than k. So either you can have these two partitions or these two partitions or these two partitions. I know. So here what we discussed is for this kind of a case where you want the first and the last partition to have median less than equal to k, it's very simple. Just iterate from left to right and keep keep the track of the median so far, whether it is less than equal to k or not. Whenever the median becomes less than k or equal to k, just stop right there. Similarly, move from right side, and whenever you find out the median becomes less than equal to k, just stop right there, and that's it. Um, you have found two partitions with median less than k, less than equal to k. Now, if there are any elements left in the middle, which you can dump into the middle partition, if there is, let's say, 7 left here, you can just say that this is the middle partition. So if you have any elements left, then yeah, you have got three partitions and two of them are having medians less than equal to k. So this is gonna be good. In case if you find out that you can't partition in this way, then that's practically telling you that hey, there can't be three partitions, right? Because you can't do anything better than this. If you, let's say, required this much of the prefix to have the median less than equal to k for the first partition, and you required this much suffix less than equal to k, sorry, median less than equal to k, then obviously if you had chosen it only this much and then only this much and this much, basically if you had chosen any other partitions, you could not have two partitions with median less than equal to k, right? Basically, if this thing is not valid for any of these, um at least you can definitely say that hey, this kind of thing would not be possible if you don't have elements left in the middle. So in simple words, you just have to check for this. Um, and talking about these cases, these are a little different. The thing is, earlier you were just checking for the smallest suffix and sorry, for the smallest prefix and for the smallest suffix. But right now, here the thing is, depending upon till which point you took the prefix, your next partition will start from the exact same place, right? So in a case like if you had taken the um, let's say if you only took this as the first partition, then you will have to start your second partition from this point on. And yeah, even if you take the whole remaining array, you would not have the median less than equal to k here. Whereas if you had chosen these two elements first and then these two elements, then this will have a median 7, this will have a median 4, which is less than equal to 8 for both of these. And for this partition, the median is 9, but we don't care. We got two partitions, right? The problem setter had given uh, this kind of an example for us, so that we can notice one thing, that um, this approach of just stopping whenever we find out the first place where the median is less than equal to k might not be good enough, right? Are you guys able to cope up with me for now? Let us see variables in first case. I can put this correspondence where the median is less than equal to k and break. So failed some test cases. Yeah, we are failing one of the test cases here with this approach. So I went to the same approach and same code, but used I equal to 0 and minus 3, j equal to n minus 1 to j plus and left, but my eliminators is not in j. Oh, glad. Okay, so see, for now, all we need to do is just figure out how we can correct our approach for this case. The same approach would be applied here. As for this case, we can't do anything better. For this case, the only thing that we need to worry about is sometimes it might be better to include some more elements even when you have already got a prefix with the median less than equal to k. So the thing that I want you to notice here is, if you have, let's say, um, if you let's say have odd number of elements in an array and you want to find out the median, it would be the middle guy, of course. Basically, the guy who is gonna be in the middle if you sort the array. Now, if you even add an element like 10 here, would it really affect the median? No, because the thing is, when you had only three elements, the median, if you sort the array, was this middle guy. Now, when you have one extra guy in the array, um, if this element comes on the right hand side, basically, if this element is greater than the median you had without this element, then the median will not be changed because we have the median. Like if you had three elements, then you would, sorry, let me use it on that next page. So basically, if you had three elements or any odd number of elements, then the median was the middle guy. Now, if you have one more guy, let's say you have one more guy who is greater than the median, then for these four people, the median is still the left middle guy. You know, this guy who was earlier middle for the odd number of elements is now the left middle for the even number of elements. So the median will not be increased. Whereas if the next new element that you have added is smaller than the median, then the median will become smaller, or it might remain the same depending upon if the new added element is also equal to the previous median. So in general, uh, what I want to say is, if you have odd number of elements, odd size of the prefix that you have chosen, and you add an element that is greater than k, then the median would still remain the same, right? So in the array, once you had found out the first partition such that the median was less than equal to k, and there is the next guy which is greater than k, taking this element into the first partition will not make anything bad for you, anything worse for you, right? Your median will still remain the same. Whereas if this guy goes into the next partition, it will either make things worse or things might remain the same. Basically, it will not make things better in any of the partitions. So since we know that keeping this element in the current partition will not make things worse, why don't we just take it in the current partition then? So what we will do is just take this element in the current partition. है ना? Because leaving it for future will either make things worse or things will remain the same. है ना? And now let's say if this element was actually less than equal to k, then you should not take it into the partition because you are already good even without that element. And if you take that element into the current partition, then you will lose the potential of having it into the next partition. So the basic idea that we have, the only normal amendment that we have made for now is, first of all, keep on iterating until you find out the first partition with median less than equal to k. Now, once you have found it, just check it out whether the current size of the partition is odd or not. If it is odd, then check out if the next element is greater than k or not. If the size of the partition is odd and the next element is greater than k, then just take it into the current partition. है ना? Taking it into the current partition is not making anything worse for you, and it may make things better for the next partition, right? And for the case if the next element is smaller than or equal to k, then you don't really need to do anything. You want the next partition to have that element, right? And you might have some doubts like, hey, what if there is one element here that is smaller than equal to k, and then there are two elements that are greater than k? There can be that kind of situations. So you can take it as a to do for you. Try to find out a case where this approach fails, and you will realize that it won't happen. If you have an element here that is smaller than k, and then you have some elements that are greater than k, then like see, if you have if you are already taking this guy, once you are already taking this guy, if you take out a smaller element and then a bigger element, then what you're doing is just losing a potential um partition that you would have got, right? So like, let's say here this was your um first partition, right? You could take an element that is greater than k and you took it, है ना? So in that case you should obviously take it. But if you think in this way that hey, the next element is actually smaller than equal to k, and then if you take this, then you can actually take two elements that are greater than k, which might make things better for the next partition. Then that's just overthinking, because if this guy is less than k, then this is one partition that you had, and the second partition will have only this one element, and you would be done with having two partitions with less than equal to k. So in a nutshell, what I want you to do is, this is a to do for you. Try to prove this approach wrong. Though you won't be able to prove this wrong, it is obviously working. I did submit the solution with this approach as well. Um, but if you try to prove it wrong, you might notice some more things, and it will help you in general for having a practice to think about different approaches during the contest. Because you see, it is very important. Let's say if you were at my place and you had thought about the approach, then you can't just go in the way that, hey, I have got an approach. Now I will just submit it to find out whether it is correct or not. Obviously, you will have to try to prove it wrong and see if you can find out a case where this is failing or not. So this is gonna be a good exercise for you for practice. Just try to prove it wrong. Okay, so let's move on to the code part. The code, I think, should not be very rough here. Okay, the code is a little rough. The thing is, here this is something related to implementation. What we wanted to do was, we wanted to keep track of the median, right? It was like you have some elements in the first partition, then you add a new element, then you want to find out the new median. And you want to do this thing with like um very efficient, in a very efficient way. So what I did is, I just kept track of the median by using two sets. One set having all the elements which are smaller than or equal to, basically, I just created two sets, and it is done in a way that even the biggest element of the first set would be smaller than or equal to the smallest element of the second set. And if I have let's say five elements, then three elements would be stored in the first set and two elements in the second set. So my median would always be equal to the largest element of the first set. Um, like this is a very standard technique. Um, if I go on explaining on how this works and all, it will take a lot of time, and it's not really required. If somebody is interested, what you can do is just search on Chrome for median of a data stream. This is a problem on lead code. This is a lead code hard problem, though it's not really that hard. It might have been hard for the standards of the problems that used to come 2 or 4 years ago on lead code. I think 3, 4 years ago on lead code. For from the current standards of lead code problems, this is sort of like a medium problem. So you can just go on and attempt that problem and then maybe look at the other solutions if you can't solve it. For now, the thing is, we don't really need to do all of this. We don't need to find out the exact median of the elements. All we want to find out is whether the median is less than equal to k or not. And we already have seen this thing once. If you have elements and you want to find out whether the median of these elements is less than equal to k or not. So for doing this thing, what you can do is, let's say you have 5 elements, 5, 1, 2, 2, 4, something like this. Then just keep track of the number of elements that are smaller than equal to k and the number of elements that are greater than k. है ना? So just keep track of this. Count smaller minus count bigger. Right? Just do this thing. So if your array is non-empty and this thing is greater than equal to 0, basically the number of elements that are less than, sorry, the number of elements that are less than equal to k are more or equal to the number of elements that are greater than k, then the median would be equal to or less than equal to k, right? Because at the end of the day, when you sort the array, half of the elements or more than half of the elements would be less than equal to k, and the median guy is always gonna be the middle guy or the left middle guy for even size arrays. So basically, it would be in this party of all the people who are less than equal to k. So this is one clever way of finding out whether the median is less than equal to k or not. I will make some amendments to my code to make it simpler. Let me do it. Oops. Sorry. So you can do something like remove all this code and just say that um, count would be maybe add this. So basically, if the element that you are adding is less than equal to k, then you will increase the count. Otherwise, you will decrease the count. And just set the non-empty thing to true. This non-empty will help us to find out whether the uh, array is empty, non-empty, and all. Though it would always be non-empty, so you can ignore it also. And um, median less than equal to k. So for this, we will just return count greater than equal to 0. So you can have your code in this kind of a way. It just made the code a lot smaller and simpler. You will have less chances of making mistakes here. We will discuss more when we come to that part. And for now, I think we are done with the logic part. Yeah, we are done with the logic part. So let me discuss it. So I took the inputs. Then to keep the code less repetitive, like instead of writing the same logic 3 times here, what I did is I created a function in which I will give a starting point and I will tell the direction whether you should go on to the right side or left side. Like either I might start from here and go towards left side, or start here and go towards the right side, start here and go towards the right side, and all this thing. Basically, I will tell from where the partition is starting and to which direction you should go for putting up the elements. And what it will do is it will keep on adding the elements. It will keep on adding elements until you get to this condition where the median is less than or equal to k. And once the median is less than equal to k, you will return the index which you had added just recently. So I will get to know about the first index for which the median was less than equal to k for the partition. So with the help of this, I can just first of all find out the ending point of the first um, partition. Then I wrote this logic of basically checking if the partition length here is odd and the next guy is greater than k, then it please include this as well. So this line will just check this thing. And after that, I'm having a few else conditions and all to just do the same thing. Find out the ending point of the next partition here. And then I'm just checking that, hey, if there are some elements left in the array, then I have got three partitions where two of them are having medians less than equal to k. So I will have to like write similar logic for the last two people for checking for the last two partitions or the outer two. This is the case of outer two. है ना? And if any of these passes, then the answer is true, otherwise false. So uh, this was just my preference that I created three functions and basically I wrapped the logic of for these three cases inside three functions and just called them in this way that if any of these is true, then return true. And um, here I'm printing yes. Basically, if you like to do everything inside the function, then you would have written something like um, bool answer equal to this and see out answer. If this is true, then yes. If it's false, then no. Right. And then move on here and delete this. So you could have done something like this also. Basically, how you want to implement it is something your choice. It's your choice. On my part, I believe I have discussed the whole logic part for everything here, and I shared a few good tricks as well. Like these tips are gonna be very useful for you in a lot of problems, um, especially this thing that if you want the median to be less than equal to k, check for it. Just check if there are this many people who are less than equal to k or not. By using this property, you can actually find out the median by using a binary search also. And at many places, this type of binary search approach is useful. Basically, if I want to find out the median of a lot of elements where there are some constraints of, like, let's say you have a matrix where the rows are sorted, columns are sorted, and you want to find out the median of all of these elements, then you can do something like just search, just check for some k, whether the median, uh, basically just find out the number of elements that are less than equal to k, which you can do easily since the elements are sorted. Basically, apply a binary search on k and binary searches for these rows and columns and find out the largest value of k such that there are at least half of the elements less than equal to k. Basically, just have some creativity in this way and you can make a lot of problems way simpler. And unsorted, I think that was the main giveaway for you for from this problem, the main learning part. And maybe you can focus on this thing as well. A lot of problems have this idea that you want two people to have something good, so just focus on these two and leave everything for the third guy. And just try to confirm it once that if you do something like this, will it always work or not? And try to focus on this thing. Will it always work or will it fail somewhere? And yeah, this is also a learning point here that in a lot of problems, the median is described as the um, m by 2 ceileth, sorry, m by 2th smallest guy. So in those cases, for the odd sized arrays, the median is the middle guy. And if you add one more guy in the array of odd size, the median would never go get smaller. It would sorry, it would never get larger. It would either become smaller or it will remain the same. This thing happens in a lot of problems. So now once you have actually seen one problem in which we solve it in this way, in future you are more likely to have this intuition. The submission for cheating, I found a person using a AI gen code. I don't know about it. I don't know if code forces do focus much on this or not. Um, anyone did E? No. D was a hard problem. I saw like even international masters, grandmaster, some of like even a grandmaster could not solve E problem, and international masters also as well. F problem was having more submissions, so I think this was the reason people went for F problem before E and could not really give enough time for E. Okay, so now we will discuss the D problem. Let me give you a quick disclaimer for the D problem explanation here first. For this D problem, my code during the contest actually gave a wrong answer. So it is um, not a, the solution that I would discuss here is not something that has actually been accepted. But I'm pretty sure that my approach or basically the idea for solving the problem is correct. Probably I'm missing out some on some edge case. So just to make sure that I'm not having an incorrect approach, I did look at a master solution as well before the PCD. Like I was just looking at the other people's code to find out if anyone is having a similar approach or not. And a master was having a very similar approach as of mine, probably the same logic. So I think maybe the problem is in my implementation. Maybe I'm having a loose end in my implementation, basically in my code, due to which my solution has failed. So in case if there is some problem with my approach that I would discuss here, please check out the pinned comment or basically the comment section. Um, you will find the correction there in case if I'm having some mistake here. Otherwise, the chances are that either the approach is completely correct or maybe I'm missing some edge case. You know, and I believe that if you are watching the PCD, it should be to learn about the ideas of a higher rated coder. That how does that guy thinks about or how does that guy approaches a problem, and not just for um, getting a problem in AC, right? So let's discuss the D problem. First of all, the D problem is defining um, local minima and local maxima. So a local minimum of an array, um, yeah. So basically, any element in an array is considered a local minimum if, like, let me explain it here. So if you have an array, then an element is considered local minimum if it is smaller than both of its neighbors. So if it is something like the element is 2 and the neighbors are like, let's say, 5 and 4, then this is a local minimum. Next condition for an element being a local minimum is like if it is a corner element, let's say it is here and it has only one neighbor, of course, since it is a corner element. So if it is smaller than its neighbor, then also it is considered local minimum. So if something like this happens, these people are going to be considered local minimums. Basically, they are smaller than all the neighbors they have. If they have two neighbors, they should be smaller than both of them. If they have only one neighbor, they should be smaller than that one neighbor. And for an array of size only one, this local minimum and local maximum thing is not defined. They have said that local minimum and local maxima are not defined for arrays with only one element. In the way as we discussed for local minima, local maxima is also defined in the same way. You should be greater than all the neighbors you have for being a local maxima. Now, the problem says that there is a hidden permutation P of length n, and the following two operations are applied to permutation P alternatingly, starting from the from the operation 1 until there is only one element left. So what you will do is you have a permutation P, like there is a hidden permutation P, which we don't have, but the jury had. He first of all applied a type 1 operation on that permutation in which he removed all of the elements of the array P which are not local minimum. So if you have an array like one, if you had an array like 1, 6, 5, 2, 4, 8, and 7, then here the local minimas are this one is a local minima, 2 is a local minima, and 7 is a local minima. You might add more local minimas, but for this example, there are only 3. So what we will do is we will delete all the elements that are not local minima. Now the new array would be 1, 2, and 7. Now in the type 2 operation, what we will do is we will remove all the elements that are not local maxima. So in this case, the local maxima is only this 7. So we will remove the 2 and 1, and we would be left up with only one element, that is 7. Right. We would be left up with only this element. So the yeah, so what the problem tells us is for all of these elements, like there are 7 elements here, 1, 2, 3, 4, 5, 6, 7. We don't know about the permutation, but we are being told, like, by the way, there's one more thing. If there were more than one elements left here right now, after 2 operations as well, then we would have applied the type 1 operation, then type 2 operation, then type 1 operation, then type 2 operation, and so on, until we have only one element left. So what would have happened is when you applied the type 1 operation for the first time, all the elements that were being removed there, you just mark 1 at those corresponding indices in this array A. Then you remove these people 1 and 2, that is these people, and the second operation. So you will apply, like you will have 2 and 2 written on those places. This guy was never removed, so you will have -1 being written at that place. We are being given this array. We are being given this array, and we have to find out any array P for which, um, like if you apply the same operations that we had applied on the hidden permutation, then we will obtain this array A only. That is what we have to do. So is the problem clear? Um, it was implementation forces. Like I think implementation was not the main thing. Maybe thinking about the edge cases was something um where we could have messed up. Like if we uh, failed on some edge case or something. Anyways, let's talk about this. So mm, yeah, so if the problem is clear, we can move on to the solution. Let me give you a 1 minute break. If you have any doubt regarding the problem, you can mention it. Oh, I am on laptop. I forgot. I was just tapping like crazy on the iPad. Yeah, there is one more thing that I forgot to mention. Um, in every operation, like on the first iteration of removing elements, you applied the type 1 operation, then you applied type 2 operation. Then on the third iteration, you applied type 1 operation, then type 2 operation on the fourth iteration, and so on. Basically, on every odd iteration, you are applying the type 1 operation. And on every even iteration, you are applying the type, right? And it can be proved that within log to n, within this many of iterations, the process will stop. You will have only one element left within the first log to n number of iterations. So the idea here is like it can be proved in a way like this. Um, in any array, if this thing, uh, since the array is nothing but a permutation, like we were applying the operations on a permutation, है ना? So if this guy is a local minima, then it means that it is smaller than its neighbor on the right and the neighbor on the left, है ना? So obviously these two people cannot be local minima. So if I'm removing the local minimas, at least half of the elements have to be removed, because there can be like two consecutive local minimas cannot exist. If this guy is smaller than the guy on the right, then the right guy cannot be a local minima, because for being a local minima you have to be smaller than both of the neighbors. And this logic will happen like um, this logic will be true for the local maxima case as well, that there cannot be two local maxima side by side. One of them have to be um, like if there is one local maxima, then the other guy cannot be a local maxima, since it is gonna be smaller than its neighbor. So half of the elements would always be removed in every iteration. So even if the size is something like 10 raised to the power 6 initially, it will become 5 into 10 raised to the power 5, then it will become 2 into 10 raised to the power 5, and so on. It will just keep on getting half and half and half. So for the problem where n the array size is gonna be as large as 10 raised to the power 2 into 10 raised to the power 5, we can safely say that there will be less than 20 iterations in total, right? And my idea here was, let's say you have an array like 1 1 minus 1. You have to find a permutation for which the elements would be removed in these iterations. So in the first iteration, everyone except the local minima would be removed. So my idea was, hey, I can just make sure that these people are the largest people that I can put in the permutation. है ना? I have to put the elements from 1 to n in this array. So my idea was, for all the elements that have to be removed in the same permutation, I will just pick up the wait, I'm getting a call. Just 1 minute. Okay, so I'm back, and otherwise stop. Okay. Yeah, so my basic idea was that I will just put up the largest people here on the if I have to remove the, like if everyone who is not a local minima would be removed, then I will just put up the largest people on these positions, while making sure that none of these become the local minima, है ना? And for all the people who have, like, who should not be removed in this iteration, will obviously stay, because um all the people around them would be the largest people. Like in this case, I will just put up 3 and 2 here, and then there is only one element left, so it must be one of us. Obviously, we got this permutation that is actually correct as well. Um, Nextly, let's talk about this permutation. Sorry, this array 1 minus 1, 1 to 1. If you had something like 1 minus 1, 1 to 1, then what we have to do is we have to remove this guy and this guy and this guy here, right? So what I will do is I will just give them the biggest elements that I have, like 5, 4, and 3, right? These people would be removed. Then I will have only these two people left. Now what I want to do is I want to remove this guy. So I will now in the second iteration we have to remove all the people who are not local maximas. So I will give him, like, let's say the value 1, which is the smallest value. So it would be smaller than this guy. Since these people are already removed, in the second iteration, you will have only these two people. I'm giving the smaller value here. So this guy would also be removed and only this guy will remain, right? So this kind of a permutation will work for um, the second test case. If you think about this test case, only these two people would be local minimas. So these would be removed. Then only this guy would be the local maxima. So this would be removed. We are gonna be good. Then the same logic will go on for the third problem, or third example also. 3, 1, 2, 1 minus 1, 1, 1, 2. So it is 3, 1, 2, 1 minus 1, 1, 1, 2. Right? Yep. So we have this case. Again, I thought the same way. 1, 1, 1, 1. I want to remove these people. And I just, at the same time, I do want to make sure that they don't become the local minima by mistake. है ना? Like in this case, in this example, when you wanted to remove these two people, you could have mistakenly given the values like 2, 3, where this 2 will become a local minimum. है ना? So you want to make sure that you don't make this mistake either. So in this case, this won't happen though. I will just give the values. I have 8 elements here, I guess. So I can just give 8, 7, 6, 5, right? For these people, I have given the biggest values. I know that I will give smaller values to these people, like who don't have to be removed right now. I will give them smaller values. So these people who are having at least one of the other people as remainders who have not been given values, um, would have someone smaller than them. So they cannot be local minimas for sure. So they will be removed in the first iteration. Then you will have only these 4 people left. Now you want to remove this 2 and this 2, right? So you can give them values like, um, right now, all the people who are not local maxima would be removed. So give them the smaller values, let's say 1 and 2. Then you will have, like among these people, this guy and this guy would be surrounded by bigger people than him. So both of them would be removed. Now we will have only these people left. This time, the ones who are not local minima would be removed. So you can just give him the value 4. And this would be given the value 3 since it is the last guy. And this is how this permutation would also work. So I hope you people are able to get the idea of how I was getting the intuition for the approach that I'm basically discussing the approach at the same time. It's more like I'm explaining through dry runs since it is going to be easier to explain and understand in that way. Let's consider this example test case now. 3 ones, then -1, then 3 ones. So here there is a catch. If you just randomly give the values like the previous case, saying that I will give the values 7, 6, 5, 4, 3, 2, then this guy will become a local maxima, local minimum. To avoid it, my idea was that since I feel it to be easy, I feel it easy to just go from left to right and keep on giving values to the um, ones who are gonna be removed now, or basically who are equal to the value 1. I just said that, hey, for the first time, like while going from left to right and giving them values, before that I will just check, hey, if the last guy that has to be removed, basically the last guy having the value 1 is actually the last guy of the array as well, then start giving them values first. I called this as a chain if there are multiple people with the same value in the row, because the thing is, um, my first intuition was just give a value 7 here, 6 here, and then start giving values like this. But that would also cause trouble as I will get another local minima here who would be smaller than neighbors. So I realized that, hey, um, this guy needs to be greater than its neighbor, otherwise it will become a local maximum minima. since this guy is already smaller than the right guy, it needs to be greater than the left guy. And for this guy, we know that this middle guy would is not equal to 1, so it would be smaller. So yeah, this order must be maintained for these three people. So um, my idea was just like put up 765 from the last in this way. Once you have filled this chain, start filling elements in the normal order as we had been doing to make sure that you don't create a local minima by mistake, right? Um, the implementation of this step was different in my case and the master's code that I saw after the contest. In that master's case, what he had done was he put elements in this way 765 432, and for the last chain that he had, he just reversed it 432 after writing it. So I don't think it should cause any trouble in terms of logic if I put up the biggest values here and then the smaller values here. Because at the end of the day, I'm still making sure that I don't have any local minima here. So probably the logic, even though it's a little different, it should still be the same. And the problem should be in the implementation somewhere. And I have only one element left, so I will just give it the leftover value. And that's it. So that was my whole logic part. The logic part that I had here was just this much, that um, whatever elements I have, I can go from 1 to 20. You know, I will have a for loop of 1 to 20. Now let's say I'm having the iteration 5 for now. Then what I will do is I will iterate over this array, or to be precise, I will iterate over to the indices where you have the value 5. For this, you can do some pre-computation to just store all the indices where 5 is coming. Um, in this way, we'll just save us a little bit of time. Um, you will actually save plenty of time, but it's fine even if you iterate with the complete array every time. And now, whenever you find 5, the idea was just check out for the last element that is present in the array right now, and basically the last element that has not been removed so far from the array. And if this element should be removed in this time, then just make sure that you give the value to this guy first and then this guy, whether you are giving the values in the increasing order or the decreasing order depending upon if it is the even iteration or the odd iteration. Start from right to left first for only the chain, and then start giving from left to right. That was my approach. um, in case if anyone can find some problem with this logic, then please mention. Baki, I think. Okay, so somebody also had the same logic and it gave WA. Okay. For now, let's um even if we assume that there is something missing in the logic, I don't think it is a waste for the PCT, because at least I did tell about my thought process and how we uh, came up to this approach. And this approach is pretty much correct because somebody passed up with the same logic. The implementation was only a very little different, or the thing that he was doing was very little different. So probably um, there is a very small loophole somewhere. And let me show you the code. Since this code did not pass, I will just skim through it and not spend too much time here. I took the inputs. I created a vector. Basically, I created a vector of integers to keep track of positions of the elements. Basically, the way in which I would be able to find out all the indices where 5 is coming, it would be done with the help of this vector of integers. I created an integer which will keep track of the place where the -1 is present, because at the end of the day, I will give the final value to that last guy. I created an answer variable in which I will just put up the answer. I created two variables, low and high. And there is an integer I created, last unvisited index. It will just keep track of the index of the element that has not been removed so far. So basically, um, let me give an example here. Mm, Yeah, so you see, in the first iteration, I would have removed these three people. So last visited index would now point to this place that, hey, this is the current last guy. It would help me to figure out whether I should start putting elements from the right side or not. And I created a lambda function with name put so that I can just call it put and give the index every time whenever I want to add an element. I'm having an assert statement that I should not have put up any element on the current index so far. And depending upon whether it's the value of j, basically which iteration it is, even or odd, I will put up the largest guy or the smallest guy so far, like the largest or the smallest guy that I have for right now into the vector. And actually, I could have written it in this way. Yeah, I could have written it in this way. Save a line. Then there is this condition which should ideally never happen. It should never happen unless you have um, got all the elements filled. Basically, all the elements other than the last guy have been filled. Only in that case, this will be empty. So you can either break here also, but just to be safe, I wrote the continuous statement here. Then this is the condition that, hey, if the last element that has to be removed for now in this current iteration is actually the last guy as well, which is present in the array, then give him the large value and his chain as well, the large values, so that you don't mistakenly create a local minima or local maxima. And after that, I started putting up elements from left to right. And if at some point of time I find out the index, which I have already put, because um, you see, if I had these elements, I did put up these people and then went for an iteration. So you will put element, you will give values to these people and then you will try to give value to this guy. So you will just break at this point because you know that you must have given values to all the people on the right hand side. And then there is this while loop to just make sure that you keep on going towards the left until you find out the last guy of the current array who has not been given a value. I gave another assert statement just to make sure that after this for loop, I must have placed all of the n minus 1 elements other than the last guy that would exist till the end. So I did put up the last guy here, and then I have this for loop. Index I, yeah, it's fine. Okay, so I'm just printing my answer here and the ending line. So the solution is not 100% correct, but I hope the idea is pretty much the correct. And in case if it is largely having some issue, if it is having some big issue, the approach has some big issue. In that case, I will mention this thing in the comment section. Either it would be in the pinned comment or you can just look at the comments. There are not too many comments in the PCDs generally. So you will find that comment. Um, or probably it would be mentioned in the pinned comment itself. And in the description, I will add my solution, the solution which I will code right after the PCD, which would be working. So what's the time? Yeah, so the time is 12:30 now. So um, maybe the code would be added tomorrow, not today, in case if I can't debug right now. Yes, I also want to sleep now. Okay, so we have discussed the solution, we have discussed the code. Does anybody have any doubt? Use the same logic also in the case of the local maxima. Did you do the operation in other like in reverse order? Like in the case you make a valley and in other case you make a mountain. Um. Okay, so you're asking like I'm doing in the reverse order, so I'm doing in the this order or not. So it's like the point behind creating the put function was to just make sure that um, the order would like whether I have to increase or decrease would be uh, done by the put function himself. Like if the iteration is odd, then it will decrease. If the iteration is even, iteration count is even, then it will increase. So I don't think there should be any problem in that thing. And let me think. Yeah, there should not be any problem there. Okay, so guys, shall we end the stream? Okay, nice. Thanks for being a part of the stream and bye bye.